Let's look at theorem 3.1 on properties of vector spaces. So let me list them first. We have that V is a vector space, so let V be a vector space. So just to be hopefully more clear, when you say it's a vector space, then all of the properties must be true. So then by definition, we have all of these properties. So we may only use these properties to prove the theorem I'm about to write up. Okay, so we have all of that because it's a vector space. So 1, the zero vector is unique. 2, negative V, the additive inverse in V, and the opposite of every vector, is unique as well. 3, if U plus V equals U plus W, then V equals W. So this is referred to as cancellation for addition, right? We don't have for multiplication, but so these are the same. Okay, so notice you have U on both sides. That's referred to as cancellation. Okay, I'll refer back to that. We're going to prove that first. 4, 0 times the zero vector is always, 0 times any vector is always the zero vector. And that's true for all V in V. And remember, we may only use the properties of vector spaces. This is something we have basically assumed forever in real numbers, right? Real numbers is basically a vector space. We know that. And we just assume 0 times anything is 0. Well, this we can prove now. 5, R times the zero vector remains the zero vector, and that's true for all R in the reals. So this is referring to basically anything times 0 is 0. But again, we can't just assume that or use other properties. We can only use properties of vector spaces, which we'll use. 6 is negative R times a vector V is equal to R times negative V, which is equal to negative R times V. And that's true for all R in R and V in V. Okay, I don't think I proved 6. So we're going to go through, and this is going to be fun to do. This is like really cool stuff. We're going to do 3 and then come back to 1. Then we'll do 2 and 4. So, and you'll see why we want to do it in that order, because we're going to need some of those other ones to prove like the first one. Okay, so check this out. So first, say proof. And let's let U, V, and W be in the vector space V. Okay, so, well, that'll be true for all of them. Okay, so we're going to do 3. So to do 3, this is it's an if then statement. So if this is true, then V has to be W. So we're going to assume this is true and then show that must be true. So do I need do anything else for R's? Well, U and V, and okay, so that's fine. So first is the hypothesis of 3. Assume U plus V is equal to U plus W. Okay. Now, because of, now remember, we're going back to all of these properties. So we're actually going to use this property, where is it? Here. We're going to use 5, the existence of an additive inverse. So we're not going to call it that yet. We just know that it exists. Okay, so we're going to say this. There exists X in V such that U plus X is equal to 0. So that's the existence of additive inverse. I'll write that down. So by the existence of the additive inverse. It's not really a property, it's a definition. It has to be true for it to be a vector space. And I was going to keep that without parentheses. Okay, so that's a vector space property. Or like axiom or rule. I probably should say that because these are definitions. Okay, we'll call it an axiom. They do in the book. All right, so then, moving on. Then we have that V plus, oops, not plus. Now we're going to use another property that we know V can be equal to V plus the 0 vector, right? There exists a 0 vector, we can write it like that. Okay, so that's, again, I won't refer back, it'll be confusing. So you can look back. So we know there exists, or we know that the 0 vector exists in a vector space, and you can say that V is equal to that. That's one of the definitions. But what we have is that zero is equal to this sum. So we have that V, that's equal to V plus, and then we can write that sum, U plus X. Right? Because we know X exists such that that's true. Now, by associative and commutative, so we can associate and commute, we can rearrange those terms and get V plus U plus X. Like that. Okay, so just, and I'll put that here by associative and commutative. Then, keep going, that equals, all right, so what is, okay, almost there. Okay, so that equals U, I guess well, okay, so both of these, yeah, this is fine. U plus V, Okay, then plus x. So that's associative and commutative right there. So all I did is associate, and now I'm commuting. Okay, following along so far? So what is u plus v? U plus v is assumed to be u plus w. So now what I have is u plus v is u plus w. So that equals u plus w plus x. Okay, now by associative and commutative again, I have u plus x plus w. Okay, and that's the same rationale, associative and commutative. Okay, so I just took this, reassociated, commuted, and then associated back. Okay, with addition, you can move everything around. There's no problem at all. Okay, now look what I have. I have that's u. Make sure these look like u's. What is u plus x? So what is that? U plus x is the zero vector. Okay, because that's how we defined it. So that's equal to the zero vector plus w. And then the zero vector plus w is equal to w. Okay, and you don't really need to conclude here because it's shown. You can say therefore they're equal, but this shows they're equal. V is equal to w, all by vector space properties. Okay, now we can use this property. That was 3, which was cancellation. So we have cancellation now. Let's look at number 1. So number 1 is showing uniqueness. So we're going to call two things 0 and then like a 0 prime and then show that they're equal. So that's how you do uniqueness, right? So we're going to choose two different zeros. We'll just name them differently and then show they're equal. All right, so let's let 0 and 0 prime, 0 vectors, be elements of V such that, and then basically they behave just like the 0 vector. So such that 0 plus V is equal to V, right? That's the same behavior. And 0 prime plus V is equal to V. All right, so this pretty straightforward now that we have cancellation, because all you got to say is that 0 plus V both equal to V, so they have to be equal to each other. So let's just say implies 0 plus V is equal to 0 prime plus V. Okay, and I can commute those. I can put it in the right order. V plus the 0 vector is equal to V plus 0 vector prime. So therefore, 0 equals the 0 prime by cancellation, right? These guys cancellation. That's the cancellation property above. We just did that. So these have to be equal. Okay, so that's by cancellation 3 above. So therefore, it's unique. So we just call it 0, of course. Okay, next one. What's the next one? Oh, it's just uniqueness of negative v, or the additive inverse. So let's do 2. So what we'll do is we'll say let x and y be in v such that v plus x is equal to 0 vector, and v plus y is also equal to 0 vectors, right? So same idea here. You're choosing two different vectors in v, and they behave the same, right? So this one plus that is 0, this one plus that is 0. And so now we'll be able to use cancellation again to show that they are the same, that x equals y. Okay, so basically you're starting off with 0 equals 0, and you end up getting that they're equal by cancellation. So that's pretty straightforward. This is something I usually would have you try again after we did the first one in class, see if you can get it. Okay, so call it negative v or negative y. Okay, so it's unique. Okay, 4 is more interesting, I think. Okay, so what was 4? So 4 is, 0 times anything is 0. Okay, so check this out. This is pretty cool. So v, let v and b v. Okay, we already know that, but that's okay. So then show 0 times a 0 vector is equal to the 0 vector. No, sorry, 0 times anything, any vector is equal to the 0 vector. Now, we know that 0 plus 0 is equal to 0 in the reals. Okay, 0 plus 0 is 0 in the reals. So let's start off with 0 times the 0 vector plus 0 times the 0 vector. I'm just starting off with a statement. Now, I'm going to say that's equal to, by distributive property, 0 plus 0 times v. But we know 0 plus 0 is 0, so that's 0 times v. Okay, but we also know that the 0 vector plus any vector is equal to that vector. So we know the 0 vector plus 0 times 0 vector. So this is where I'm just stating a property of vector spaces. Okay, actually I found it by definition 4. Okay, well, what does that give us by cancellation? So check out. I got this is equal to this. So these are the same. Let me show you again. These are the same, so by cancellation, that has to be the 0 vector. Therefore, 0 times any vector is equal to the 0 vector by 3 above. And that basically shows why 0 times anything is 0 for any vector space, which includes the real numbers, which I think is kind of cool. All right, so now these proofs are here. This is something I probably have you just like redo, like copy it. I don't care. Just you got to go through this again. Some of these techniques you'll see again later, especially if you're in math major. If not, I want you to see how to prove stuff for once.